Hey, I'm Trent Robertson from the University of Hawaii at Manoa. I've got another walkthrough today that's going to cover the design and fabrication of a simple sensor module that you can use in a lab setting. I'm working on a project for REES Hawaii, the Renewable Energy and Island Sustainability, and they want to sense various attributes of rooms and be able to collect this information somewhere. So in order to prototype a device to do this, I think it would be convenient to put all of the necessary sensors onto a single board, bring them as close together, and mill out a PCB so that we can have just a row of pins that we can connect into a microcontroller or something so we can start the software development afterwards. So in order to do that, we're just going to pull out a light sensor, which we'll have to put in series with a resistor, because this is a variable resistor that changes its resistance based on how much light is incident on it. So we'll put power on that end and ground on the other, and this is going to be one of our outputs. We've also got a temperature sensor. I'm using the TMP36, and I'll hover my mouse over these pins and it'll tell me what they all are. So we got voltage, output, and ground. Okay. And I'm also using a microphone breakout board from SparkFun. And if you click on a part from a common distributor like SparkFun, typically they'll have a lot of information in the inspector, and you could even click on a schematic or a data sheet for this part, and it'll pop up in your internet browser. So I'll pull that out. Okay, this is voltage. That's ground, and that's going to be our output. Okay. Now we'll put on some female headers. I tend to put these in by default, even if I intend to actually put male header pins there. It doesn't actually affect the design. Yep, okay. Now, I don't really have any specific strategy to recommend for this. It just kind of comes from having done it a lot. Let's see, this should be connected to voltage. Why isn't it? Oh, I missed. Okay, that's better. Wow, that looks good. Okay. Just gonna bring everything in a bit closer. Because the less material we use, the faster it'll mill and the cheaper it'll be to fabricate. Okay. Oh, I forgot to connect the two sides of the breadboard. A very realistic problem. Wow, that looks good. Okay. Alright. I don't think I could squeeze those together much more than that, so I'm going to go ahead and bring the PCB size down. Okay. Wow, that's even smaller than my first attempt, which I had this on the side to kind of guide me. And I made this earlier, and this is actually bigger. Doesn't look quite as neat. Well, anyway, I'm going to go ahead and save this. This is going to be sensor module 2, I guess. Export that. I'm going to send those files over to the milling computer. Alright. Oh man, remote desktop is awesome. Thank you, TeamViewer, for free non-commercial use. Seriously, your software is great. Okay. This is the circuit that we did yesterday, and conveniently we can use this as a guide for where to place our next circuit on this PCB. So I'll just go ahead and leave that in there. We'll import the new files. I always pick the top one, and it tends to be right. Okay. So here's our tiny little circuit. As usual, first thing we're going to do is isolate. We'll pick our copper. Nope, that's our last project. Copper 0. We'll use the same 15 mil. And we'll go ahead and hit isolate. Just zoom in and check to make sure it actually got in all the little spaces. I think having multiple circuits in the project is just killing the program right now. Uh-oh. Okay, this is a good thing to demonstrate. Over here, this gap was too small for the bit to fit in there. But we can clearly see that if it went in there, it wouldn't really damage the design, you know, and it wouldn't break anything. So what we're going to do in this case, if you see something like that, we're just going to isolate it again, but this time we're going to actually check the force isolation box. Now, if you had SMD components, this would pretty much destroy the pads. So this is only a good idea to use in situations like this, where the bit could totally get in there and it wouldn't ruin the trace on either side. So we'll select that same layer, hit isolate. And you can see it went in that gap, and that's not going to damage anything at all. Okay, so next up is the drill holes. So we'll just reset these at 40 each. And this time I'm going to do the contour router a little bit differently. I showed you one method last time, but I said there are a couple. So I'll hide all my layers except for my new contour. So we'll edit this. And you select it. You go to edit, convert to polygon. And now you can isolate this polygon. In this way you'll actually get the exact size that you had programmed, whereas the method I did yesterday, it would actually bring in each wall of the PCB by half of the width of the drill bit, or the contour router rather. So basically it would be 10 mils in on each side ish. But this will make it perfect. So we're gonna isolate our contour layer with a 23.6 contour router. Okay, now we're going to edit all. One last final inspection. Everything looks good, but I'm thinking I might just want to rub out this extra copper just to make sure that I have no problems soldering. So in order to do that, you're going to select your copper isolation layer, and you can tell it's an isolation because it actually has a bit in parentheses. Make sure that's the only layer that you have on edit, and we're going to select this rub out tool and just click and drag over the whole circuit board. Now the bit's going to go in and remove all of that copper, so the only copper on the board is what's necessary for these traces. Okay, now we're going to combine all our layers. So this is garbage. This is our isolation with the forced isolation. This is our contour, and that's our rub out, and that's our drill. Merge that. And this is going to be bottom. We'll mirror it so that we solder our components into the top. Hit OK. And now we need to move it before I start milling it. So that's where our previous design was. I can just stick it right next to it, and I'll put it out here. And I'll move the contact by touch to be closer to this one. And I've already initialized the mill, so we'll just go ahead and run that layer. I'll put the end mill first, and then it'll drill, and then it will cut it out. Okay. So here I'm about to solder majority of the components on. I'm going to put the microphone on after because it's going to have to go backwards. So we'll go ahead and get started on this guy though. Well, there's the sensor module with light, temperature, and sound, all conveniently broken out into a bunch of pins. So here I have our new sensor module and an Arduino. I'm just going to hook them up real quick. Gonna plug our ground into that rail. I'm going to put 5 volts in there as well. And all of these 3 are going to be analog inputs, so I'll put that A0. Temperature is going to be A0. Sound is going to be A1. And light is going to be A2. Okay. That's hooked up. Now let's write some code to see if this module actually works. Here I have a basic Arduino program that I put together to read this sensor module. So I'll just kind of walk through what I've got here. At the start I've got my universal variables declared. The first 3 are the pin numbers that I've connected each sensor to, that being the temperature sensor, light sensor, and microphone. This is going to be the temperature as it's read, and this is going to be a converted to Celsius temperature based on the voltage at this pin. So after that we've got our final light and sound values, and we're going to end up buffering each of these inputs to try and reduce noise. So you can change the buffer size here. I've got 10 samples right now. We're going to be outputting these values over serial. So the program starts, goes through a read sensors program, and I went ahead and stuck a averaging buffer in. So that function starts by creating these buffers, initializing the sums so that we can take an average at the end. And in the loop it takes a reading, the sound takes a reading from the microphone port. This minus 512 is there because this wave will be oscillating at about the halfway line, and that would be at 512. So we're subtracting that out and taking the absolute value to get the sound power level essentially. We could multiply this by 2 to get the full 10-bit range if we wanted to. Then we add up each value as we move along to get a complete sum. We do the same thing with light, except we don't have to do any subtraction or anything. We just take the value. Same with temperature. And then we take the average with the sums that we calculated. After that, we convert the temperature to an actual Celsius based on this little factoid right here, 10 millivolts per degree Celsius. So after that we print the values over serial, and I'll show you what that looks like. I'm gonna just cover the module with my hand, and you can see the light level goes way down. I'll take my hand away. Oh, I screwed up the program. It's giving us the temperature, I mean the raw value instead of Celsius. Microphone, if I tap it, values are a bit bigger. It's still got quite a bit of range to it, but as long as we know that, we could put it through a low pass filter, and that should smooth out the sound levels. So there you have it. Very simple Arduino program for a very simple circuit that was fabricated using our rapid prototyping facilities. I hope you found it useful,